I'll just give you a little bit more in detail about what Manuela said. This is just like an update, but with a little bit more detail on what part has done what. So let me just talk first about the pre-merger. So as Manuela mentioned, the plan is to do everything from the pre-merger to the post-merger of binary neutron stars. And the way to do it is link different codes. So the first thing that we'll do is we get the initial data from Lorraine, and then we evolve it using Illinois GRMHD. So the update for Illinois GRMHD is that Leo has done a lot of incredible work, and now we have Illinois GRMHD working with the tabulated equation of state, which is really, really cool. It already evolves electron fraction and entropy. And also, it has a neutrino leakage scheme. So all of that is new. It will be open source very, very soon. And we'll just work with that. So here are just some results. So here's, for example, a convergence test. So these are all tests done to test the equation of state and the neutrino leakage scheme. In this case, just the tabulated equation of state. But here is just a convergence test for a single neutron star, and everything is compatible, everything works, it should converge. So we're basically good with that. And to test the neutrino leakage, what Leo used is just a relatively simple fission on Queequeg fission disk, unmagnetized, but it does lead to a slightly different disk cooler system, but still it's pretty good. So everything has already been tested. And in particular, the neutrino leakage scheme, as you can see from here, it actually does Illinois GRMHD does a pretty good job. And here I'll just show the movie. So this is a magnetized and equal, this is a binary neutron star, and it has everything. So let me just play this really, really cool movie. So this is what we'll use as initial data for the next run. And everything will be done with this NeRPi, this new NeRPi package, which you can learn a little bit more, and it'll be open source. So this is all really, really cool. And this will be the initial data to then the post-merger. Now, let me just give you an update on the handoff. So if you want to learn more about the handoff, I highly recommend Fede's paper. So it's really cool. Fede did an amazing job in the handoff. And you can also check out Fede's APS talk, because it can get really highly technical, of course, but it's, of course, extremely nice. And let me just show a movie. I think Zach already showed this movie, but it's a really nice movie where you can see the transition between Illinois GRMHD and HARM. So first, in Illinois GRMHD, it has adaptive mesh refinement, but it has Cartesian grids, which of course are very diffusive, and they don't conserve angular momentum. So first we'll evolve the binary neutron star in Illinois GRMHD. And then once the black hole forms and we have the torus, that will be passed on to HARM. And you can see, so first this is Illinois GRMHD. I'm going to pause it right here, but then it'll transition onto HARM 3D in a very seamless way. So you won't notice the difference there. So now this is the grid that we're going to be using in HARM 3D, or rather at least one grid that we can use in HARM 3D. And you can see that the transition is pretty seamless and everything is really, really nice. So this is basically the same torus, and then we evolved it in HARM 3D. The nice thing about HARM 3D is that we can use an arbitrary grid system. So for example, we can use spherical coordinates, which makes it way less diffusive, which is what we want for these types of systems. So I think, yeah, you can also see this movie, which is the other angle. You see this in Illinois GRMHD, and then it'll go into HARM in a very seamless way. There you go. So of course you can see all kinds of tests in Fede's paper, but for now I'll just leave you at it. And what we'll do next is the post-merger will be done in HARM 3D plus Nuke. So I'll redirect you to this paper in case you're more interested, or of course you can ask me any questions. But the nice thing about HARM 3D is that, as I told you, it can handle any arbitrary coordinate system. So we can have crazy grids like this one that has a really nice resolution in the polar region or in the equatorial region near the torus. HARM 3D is fully parallelized, it is very well tested, and it has copious analysis tools. And HARM 3D plus Nuke, which is the newest version of HARM, already has tabulated equations of state and a neutrino leakage scheme. So again, if you want to see the tests, you can see the paper. And just let me show you one really cool thing with Harm 3D. So this is a movie of a magnetized fission Moncrief torus. So here's the torus. I don't know if you can see it. It's this really, really tiny spot. Here's just the electron fraction. And it will be evolved both with an equation of state and with a neutrino leakage scheme. What's really nice is that the treatment of the good treatment of energy of density and temperature at larger, at very high density. So the good treatment of an equation of state is going to drive a wind just due to the fact that there is recombination from alpha particles, dissociation of alpha particles to free nucleons, and that drives a really powerful wind. And of course, the torus is also affected by the neutrinos because the torus is going to be cooled by neutrinos. And the electron fraction is going to be also affected by neutrinos. So again, if you want more details, you can ask me, or you can check out the paper. But let me just also show the disk thickness as a function of radius and the mass accretion rate as a function of radius for the simulation of a magnetized torus. So right here at around 100 kilometers is where the dissociation happens from alpha particles to free nucleons. So here we have alpha particles in the disk, and here we have free nucleons. So this basically drives a really powerful wind, which is very important to consider for simulations. And the inner regions of the disk are going to be highly affected by neutrinos. So this disk is going to get thinner just due to the fact that it has neutrinos. And here, if you notice in the mass loss rate, this is a function of radius. In here, negative means that the wind is going outward. So here in the inner regions where neutrinos dominate and not the dissociation, you can see it's just a normal mass accretion rate. But at 100 kilometers more or less, where you see this dissociation wind, you can see this outflowing from the torus. And all of this is extremely important to consider if we want to realistically do the simulation of a binary neutron star, as has been proven by everyone in this conference. And just for completion, I want to show the luminosity as a function of time of the different species of neutrinos and the mass accretion rate to the torus as a function of time. And what I want you to notice from this plot is that, not surprisingly, as material falls from the torus to the black hole, it is heated and neutrinos are formed. So the neutrinos follow the mass accretion rate pretty nicely, which is again not surprising, but it's just a really nice result. So all of that we'll be using for our production run. So this was again a fission on Moncrief torus, so no realistic conditions, initial conditions yet. But now let me show you the production run 0. So this already has the initial conditions from Illinois GRMHD, then passed on to Harm 3D plus nuke, and evolved for several milliseconds. So I'm going to show first the density, and here's also the magnetic field. I don't know if I can play them at the same time, so I'll just click one and the other one right away. Let's see if it works. So this is evolving in Illinois GRMHD, and after some time, it's passed on to Harm 3D and evolved in Harm 3D. So this is what we have so far. Oh, I don't know why it stopped. This is what we have so far in our simulations for the production run, but this is still working. So this is still being run in Frontera right now. So we have, I think Manuela mentioned, up to like 90 milliseconds, but we want more, of course. Now, these are non-published results, but let me just tell you a little bit of things that we have learned, or a little bit of things that are still open questions for us. So first of all, here what I'm showing is just the magnetic energy as a function of time. And this is for a run that only has a polytropic equation of state. So this is a polytropic equation of state. And this is for the run that has a realistic tabulated equation of state, in this case, slide 4. So what we found is that there is enhanced growth of magnetic energy compared to this polytropic equation of state. We still are working on learning why, but it probably has to do with some neutrino dissipation, because this run does not have neutrinos, whereas this one has. So it probably has to do with that. And here what I'm showing is just the magnetization. This is at different times. So this is at the beginning of the simulation, and this is a little bit later. So this is at almost 60 milliseconds. And you can pretty clearly see that there is enhanced growth of the magnetic field. So of course the question is why? And we still don't understand it perfectly. We're still trying to understand why. So, and just a little to tell you a little bit more about the magnetic field. So if we decompose the magnetic field in toroidal and colloidal, we can do it in 2 different ways. We can do it in terms of the fluid velocity, which is this way, or in terms of the coordinate vector. So what you're looking at here is in green, in blue, you're looking at the total magnetic energy. So it's this curve right here. In red, it's the parallel component that could be interpreted as a toroidal component. And in green, it's the orthogonal component, which would be the colloidal component. So far in our simulations, the toroidal magnetic field dominates a lot, which means that there is no jet so far. But we expect the colloidal component to increase, and then we'll be able to see the jet. Another thing that we have noticed is that, so the time step in this production run is going to be limited by the extent in the phi cell. So we're actually going to try a new grid that should run 10 times faster, which is really, really nice. This is again a work still in progress, literally as of this week. I think Fede has starting to see some results. So I think he can talk about that, but this is still ongoing. So all of that is still ongoing, and we're still working on the production run and on interpreting the production run and all the results. So keep tuned on that, because we're going to have some nice results, hopefully in a few months. Now, of course, for future work, as Manuela mentioned, what we want to do is, now that we have the runs, then we're going to start to analyze them. So what we want to do is, first of all, we want to do nucleosynthesis with Skynet, because of course we're going to have this very interesting disk outflow that needs to be, that we need to figure out what are the abundances. We also want to explore more equations of state, and of course, as the jet traverses through the medium, it's going to encounter this disk wind, and we want to understand the interaction of the jet ejecta at very large distances, and the subsequent electromagnetic emission. So all of that are things that we want to do, and that we'll be able to explore with this run just in the future, once we have the jet and once we can analyze everything. So again, keep tuned, because all of this is going to be done, and they will be very, very cool and interesting papers. Now, those are the conclusions for this part, and I wanted to talk a little bit about a different project that I've been working on. So this is a different project again, and speaking of the interactions of jet with ejecta at very large distances, this is a project that I've been doing with collaborators here at Northwestern. So I'm going to talk about jet ejecta interactions in 3D. This is a paper mainly done by Or Gottlieb. So here you can find the paper. So again, as you all know, if we have a torus and we have a black hole, material from the torus is going to fall due to magnetic instabilities to the black hole, and that is going to drive both a jet and several disk winds. And we of course need to simulate that and the interaction of this jet with the ejecta. So this is what we did in this paper. So we use Hammer, which is a GPU accelerated version of HARM. It's, I think, 1,000 times faster, so it's pretty fast. And what we did for the simulation is just we initially put a fission on torus surrounding a black hole and a dynamical ejecta in the background. So the dynamical ejecta, it has an analytical angular density profile that's based on GW 170817, but everything is analytical. And we, of course, vary the parameters of the density. And the torus has a toroidal and a colloidal magnetic field. Well, I mean, different simulations have either toroidal or colloidal magnetic fields. So what's really nice about the simulations is that, first of all, they're in 3D. Then, because Hammer is very fast, we can do very large distances. So this simulation is done at very, very large distances. And the other nice thing is that we start from the torus. So the majority of the people impose a jet and then see the interaction of the jet with the medium. But here, since we put the torus first, the torus is going to form a jet. So the jet is going to be self-consistently launched, which is really nice. So of course I need to show a movie. And let me just say first that we found that there are three main cases of things that can happen. Again, this is not surprising. So first of all, if the jet is going to form, and if the jet is powerful enough, it's going to break from the dynamical ejecta, and we're going to see a successful gamma ray burst. Now, as the jet plows through the matter, excess material is going to be accumulated in this cocoon. And in the case of a successful jet, the cocoon is also going to be successful, and we'll be able to see the emission from both jet and cocoon. Now, it could be the case that the ejecta is powerful enough that the jet gets choked, but we form the cocoon, and it could be the case that the cocoon survives. So that is case number 2. Or the ejecta could be dense enough that both jet and cocoon gets choked. So those are the main 3 cases. And here I'm going to show a movie where both the jet and the cocoon are successful. So let me just press play. This is a movie of the proper velocity, but it's really cool. So you can see a jet being formed in the cocoon, and then it breaks from the dynamical ejecta and just starts to expand freely. So it's a really, really nice movie. And then let me show a movie. This is a movie where the jet is going to be choked by the ejecta, but the cocoon is not going to be choked. So you'll see that the jet is going to be trapped, but the cocoon is going to continue to expand. And we'll also be able to see this emission. So here the jet is not powerful enough, so you only get to see the cocoon, and the cocoon actually breaks free from the ejecta. And we'll also be able to see this emission. We should also be able to see it. I won't show a movie where both of them get choked because those cases are, of course, not that interesting. These 2 are the most interesting cases. And here's just an analysis of the simulations. I won't go into a lot of detail. We performed all these different kinds of simulations, so we have all the simulations. Here's just the mass of the dynamical ejecta. Alpha and delta are parameters of the dynamical ejecta and on how they vary with angle and with radius. TD is the delay time between the formation, between the neutrons, the merger of the neutron star itself and the formation of a black hole. This is just the minimum velocity of the dynamical ejecta. We, of course, change the magnetic field, so we have both toroidal and toroidal components, well, simulations. This is just the plasma beta parameters, and these are just results from the simulation. So this is the breakout time, and this is the energy of the cocoon. Here I'm showing the mass accretion rate as a function of time, the bound mass as a function of time, the efficiency of the jet, and the luminosity of the jet. So what I know that this plot is very loaded. So what I want you to take away from this plot are, well, several things. So first of all, if we notice the plot of the efficiency as a function of time, we see that in almost all cases, we have a very powerful jet that is very, very efficient. And these jets are actually magnetically arrested jets. So we do get to that regime. And these are, of course, successful jets, whereas there are cases in which the jet is unsuccessful. So these are all these cases. Then another very interesting thing that we found is that these models right here that have MB in them, so for example, focus on the green model, they have bound dynamical ejecta mass. So some of the dynamical ejecta is still bound to the black hole. And in those cases, what's going to happen is that the mass accretion rate is going to be dominated by this bound component of the dynamical ejecta. The problem is that the dynamical ejecta is unmagnetized. So if that is the case, and the majority of the mass accretion comes from an unmagnetized ejecta, there is not going to be a jet. So the jet is going to be suppressed, which is also really interesting. And you can see it from the efficiency right here. I mean, you basically have no jet. What we also did was we then took the results from the simulations and got the energy profiles as a function of angle, and also the energy distribution as a function of the proper velocity. And this is just the jet's magnetization and how much energy you have with a certain magnetization. So from this plot, what we can take away is that this is just the energy as a function of angle. You can see that in all cases, we see that there is a very flat core that then decays as a power law. So this is a really nice result, and this hints that the dynamical ejecta is not the responsible one for the shaping of the jet, but actually it's the disk wind. So for example, the wind that we've been discussing in the TCAN before, so this very powerful outflow, that is going to be most important in shaping the jet itself, which is really, really nice. From this plot, we can see the mixing of the material with the cocoon and the medium. And what we can take away is that there is very low mixing in a successful jet. And from this plot, what we can see, this is just the energy that has a certain magnetization, and this is just the magnetization itself. What we can see is that if the jet is successful, the jet will remain really highly magnetized, which is very important because the majority of the studies deal only with hydrodynamical jets, but we need to deal with jets that also have magnetization in order to be consistent. And just for completion, I'm just showing a plot here of the luminosity of the jet as a function of time. This is all for all the models that I can actually calculate a jet luminosity. And what I want you to notice is that, first of all, not surprisingly, all the different models lead to very different distributions of the jet luminosity. And also you get this variability of the jet, which is really cool. So the main conclusions of the paper are that the jet is going to be successful if the dynamical ejecta has very small bound mass or no bound mass to the black hole. There is a strong vertical or poloidal magnetic field, and the jets are mainly shaped by disk winds, not the dynamical ejecta itself. They will remain magnetized. And again, this is not surprising at all. If the magnetic field is toroidal, it is going to be very hard to launch a jet. You're going to need very, very, very high magnetic fields, like plasma beta of 10, which is a little bit crazy. So thank you very much, and please let me know if you have any questions, both about the project or about this paper, and thank you very much.
All right. See if there are questions. Again, please raise your hands. I guess while you're preparing your questions, I'd like to ask one myself, which is, in these jet simulations, the luminosity of the jet depends on a couple of things that you sort of put in by hand, like the spin of the black hole, for example.
Yes, of course.
How much poloidal flux you place in the inner regions of the torus.
Yeah, so the poloidal flux is, I mean, we vary the plasma beta parameter, which of course the poloidal flux, I mean, you're totally right. And we fix the black hole spin, I think it's 0.8, if I'm not mistaken. But yeah, you're absolutely right. Like, all of this are just results from our simulations. We do plan to explore more parameters. So this was just the initial simulations, but we have the two lead graduate students, so Teresita and Serena. They're going to be performing lots of more simulations, exploring also the dynamical ejecta, because this was with only one mass. So we want to vary the mass of the dynamical ejecta, for example. So I mean, you're totally right. I agree. And it's going to be very interesting to vary all these parameters.
Okay. Are there more questions from the audience? See, Amir.
Yeah, I have a question about when you say that the jet remain magnetized, you mean after breakout or at large distances?
Yes.
By the way, what's the sigma? I mean, your magnetization is limited by density flow, right?
Yeah, so I think so. The maximum sigma should be like 100 or something like that.
100, okay. So
Really,
so if it's magnetized upon breakout, then it means that, you know, such a jet will not radiate.
What?
You need to dissipate the magnetic energy to have radiation eventually. So
yeah, no, I mean, magnetic reconnection is going to be very important. I agree.
Reconnection by what? I mean, this in this region, the jet is already acausal. If I understand correctly, you know, after breakout, it expands conically, so it means it's acausal. You cannot have reconnection. I mean, you need some sort of instabilities, unless you have some, you know, field reversal to begin with. So these instabilities must, you know, occur in region where the jet is causal, collimatum or something. And actually, many studies show that. I mean, they don't find such kink instabilities or so. So I'm wondering, there seems to be like some missing physics still.
So I think that the jet is I mean, it's magnetized, but I don't know if it's highly magnetized. I don't know if it gets to the maximum sigma. So let me just get back to you on that, because that's a really good question. Let me just see the different sigmas. But that's a really good question.
Are there more questions? About Ari's results on jets or on the handoff and our plans for furthering these science runs, or for the sort of overview that Manuela gave? Looks like the end of a long week, exhaustion has set in. If that's the case, then let's take it's about a 10 or 15-minute break, and we'll open the final session, the last discussion session at noon, led by Hirotaka Ito and Amir Levins.